Hello, my name is Madeline Olson. I am a senior software development engineer at Elasticache, which is the managed Redis service, a part of Amazon Web Service. And today I'm going to be talking to you about a brief history of encrypting your Redis traffic. So let's start with the agenda for today. So I'm going to be talking about what is worth telling about this specific story, which is about how TLS ended up in Redis 6. Next, I'm going to be talking about a little bit of fundamentals to sort of motivate the conversation, which will be what is TLS and why is it used, and how and why have Redis users secured their database before native TLS. So with that sort of fundamentals in place, then I'm going to jump right into the adventure of adding TLS to Redis in 3 parts. So let's start with why do I think this is important? So I have a very long history with TLS and Redis. At AWS, I focus on security and open source. So this was sort of a natural thing for me to be involved in. So AWS, we submitted the first comprehensive pull request for integrating TLS for Redis right before the RedisConf of 2018. We talked about it at the RedisConf and we were really excited. And we were really excited to go to Salvatore and hopefully get that merged in. As some of you may know, Redis 5 was being announced right around then, and we were hoping to get it into Redis 5, but that didn't quite happen. And we ended up sort of prototyping a little bit after that, and so I was the one that spent a bunch of time. I submitted 2 prototypes, sort of kind of evaluating different options. But ultimately, we went back with something more similar to the original approach, which I'll call the V2 design, and I ended up getting credit as one of the smart folks from AWS, which I am a little proud of. So given that history, why do I think it's important to talk about TLS and Redis? So TLS has been a major feature ask for Redis, but it's been ignored in favor of a lot of other simpler, more applicable features. And I think it's worth talking about kind of why that's changed. So one big thing is security. Redis 6.0 has ACLs. Security in general has become a lot more important as compliance has been distributed more widely, and also because there's been a lot of recent security vulnerabilities and security breaches. So I think just the general security consciousness of the community has risen a bit and has put more pressure on actually developing the implementation. However, I think the more interesting thing to talk about is the iterative approach that was taken to finally get to the actual solution and how that sort of exemplifies how Redis was developed. So I think it's worth talking about the several design phases that we had, sort of the pitfalls we found along the way, and how we ended up at the solution we did. So with that in mind, let's start looking into some of the fundamentals so that I can explain what's going on with these implementations. And to start, I'm going to go over what is TLS and why is it used. So TLS, formerly SSL, as some people will continue to call it, is a cryptographic protocol for negotiating and sending secure information. TLS is predominantly used over networks that aren't considered secure, so things like the World Wide Web, but can also be used on secured networks to sort of add another layer of security. So TLS is a form of encryption in transit. It's where you can protect your data while it's being sent from one host to another, and this is useful for protecting the integrity of user data and also making sure sensitive data isn't leaked. This is often a requirement for many types of compliances like GDPR, HIPAA, PCI, etc. So there's many reasons to use TLS, but of course that means there's also some drawbacks. You don't get it for free. The main limitations are usually centered around performance. Since it has to do encryption-based operations, that's going to inherently take CPU time. Additionally, it also increases the amount of connection time since TLS requires a negotiation phase where it's sending data back and forth, which happens before you can actually go and start sending your user data. So these 2 specific issues tend to hurt Redis-specific use cases, since Redis tends to focus on applications that are high throughput and low latency. So there has been some recent advancements to help mitigate these issues, specifically around there's been some hardware improvements so that some of these encryption algorithms can take advantage of this hardware acceleration. Also, the latest version of TLS 1.3 removed one of the necessary round trips in order to establish a secure connection. So there's been some improvements, but there are still sometimes other applications where you might not want to do this. Instead, you might want to rely on other forms of security, maybe just encrypting the data at rest within Redis, and that will meet your application needs. So now that we kind of understand what TLS is, I want to talk a little bit about some internals of Redis. I'm not going to talk about kind of what Redis is. Hopefully you guys are all familiar with that. But I'm going to talk a little bit about some specific internals that I think are needed to understand how to build a network implementation. So the first thing I want to talk about is the difference between inbound and outbound connections. So the connections that most users are familiar with are client connections, where a client connects to Redis, and Redis will accept that connection and start processing user queries. In this scheme, we're calling that an inbound connection, which is a connection that Redis did not initiate and just needs to accept. So the next type of connection we want to talk about, which differs slightly, are replication connections. So replication connections are defined by the replica reaching out, an outbound connection, to the master, which accepts as an inbound connection. So the replica needs to know the address of the master so it is able to successfully create that outbound connection to it. The master actually accepts this like a regular client and waits for specific commands to be sent by the replica in order to identify it as a replica. So the last type of connections are the cluster bus connections. So in a Redis clustered configuration, Redis contains the information to talk from every node to every other node in the cluster. This is used to send gossiping information so that nodes can do failovers when one node becomes unavailable. So there's not quite the same relationship in the replication connection, since nodes are either have already established an incoming connection or they'll go and proactively establish an outbound connection to another node. So in this case, there's both inbound and outbound connections. So the next basic concept I want to talk about is the Redis event loop. So Redis is built around the idea of a single-threaded, polling-based event loop. So Redis polls events from the kernel using an interface like epoll or kqueue, which are interfaces that allow Redis to request or to receive events about when sockets can either be written to or have data to be read from. Redis then can register what types of handlers it wants to call based on whether or not there's data to be read or data to be read out. So that's a little bit complex, but to give a concrete example of that, when Redis starts up, it opens a port and asks the kernel to notify it when an inbound connection is established on that port. When a client attempts to connect, the kernel will notify Redis that there's data to be read. Redis will then set up a client and replace the handler with one that processes incoming requests. So now when future data comes in, Redis will then call the new corresponding read query handler and continue on. So these handlers drive everything within Redis, from client handling to the cluster bus to replication. The Redis event loop also supports periodic jobs that are triggered based on a cadence, which is able to handle the async jobs that Redis does, like disconnecting old clients, expiry, and updating service info. Cool. So now that we have all the Redis fundamentals, let's start talking about how the users of Redis used to encrypt their traffic before native TLS was developed. So the most common way to do this was what we call a TLS proxy. Something like stunnel was commonly used. So the way these TLS proxies work is they would be responsible for handling all of the TLS negotiation and sending and receiving of encrypted data, and it would be entirely contained within a separate process. So let's look a little bit at how this would be configured. In a simple case where you just have a single node and all you need to do is accept client connections, you would have a host, you'd install Redis on it, and you would open Redis to have a single local port. You would then create this proxy, and it would be configured with an external port, and it would know that it needs to proxy all of the external port to the internal Redis port. So when an inbound client connection comes in, it would do the TLS negotiation before Redis is aware of the connection, and then once it's complete, it would open the connection to Redis. At this point, Redis is aware of the connection, but isn't actually aware that there's a proxy in between it and the client. The only thing Redis is aware of is there's a local connection that is sending it traffic that it should respond to. At this point, it's basically a transparent way to add TLS into Redis. So this case works well, but then it gets slightly more complicated when we add in the outbound connections we talked about. So in this case, Redis still has to talk to its local proxy when it wants to establish outbound connections. So the proxy needs to be configured with every possible address it could possibly connect to. In this case, the replicas proxy needs to know that if you connect on a specific port, it will connect to some specific remote master. This means that when configuring Redis, you need to know not what's the remote address, but what is the local address you need to connect to that corresponds with the remote address. And this way, there's sort of a map that's created within the proxy configuration to connect multiple nodes together. So in this case, it can't just exist within the replica, because in the case of a failover, the node still needs to be able to connect to the new master. So this tends to work pretty well until you get to some of the large clustered configurations. Redis advertises that it can have up to 1,000 nodes, which means that every time you add or remove a node, you need to go and update every node in the cluster so it's aware of all other nodes. If you were to say misconfigure anything, 2 nodes may not be able to talk to each other since they won't be connecting to the right ports. This tends to be a configuration challenge once you kind of get to scale. So just to kind of summarize the state, so a TLS proxy is a separate process for managing TLS. There's a very high complexity in configuring them when you get to large clusters, and there's also an increased CPU cost. If you think about it, this process is handling additional read and write requests without actually doing any work. It's just sending the data to a different location. We'll talk a little bit more about that later, but that will actually end up being a relatively large drawback. Okay, now that we have all the fundamentals established, it's time to jump into the adventure of adding TLS in Redis, part 1. A new implementation. So I'm going to briefly kind of go over what our AWS's original implementation was and what motivated us behind making all of these decisions. So our initial approach to implementing TLS in Redis was to have everything be done on the main Redis thread. The goal of this was to try to get as high of efficiency as possible with CPUs, since we wanted to not take as much away from our customers as possible. Right? No one likes to use a single thread process and not be doing anything with it. So what did we need to do to accomplish this? We needed to implement effectively 2 main parts. We needed to be able to handle the TLS handshake for both inbound and outbound connections before processing or sending data. Ideally, this should somehow integrate with the event loop. We didn't want to be doing blocking requests while TLS was being done. The next thing we wanted to do was to be able to maintain TLS context for connections and then call the respective TLS read-write functions instead of the TCP-based read-write functions. So, although this is kind of the high-level picture, there's a couple of specific low-level problems we ended up needing to solve. The first of those low-level problems was that Redis uses file descriptors as a way to define connections. So, as we said, we need to have some extra metadata in order to say, when you call the TLS write, you also need to pass in that metadata. However, Redis really only has the concept of file descriptors. So one thing we could do was basically bifurcate all of these APIs, have a sync TLS read, or we could find something slightly better since we didn't want to duplicate all that logic. So the solution we originally came up with was to use what we were calling wrapping functions. So if you aren't familiar, in GCC, you're able to wrap functions to be able to basically replace already compiled libraries and pull out those and provide your own implementation. So in this case, every time there is a read in the source code, we replace it with this wrapped read function. And if you look at this wrapped read function, it's pretty straightforward. We check if we can wrap it. If we can, we check if SSL is enabled. And if that's true, and there's an SSL file descriptor, then we call the real SSL read function that we have. Within this function, we had a map between file descriptors and TLS contexts. And we'd go and look up that TLS context and apply it during the TLS read. So this ended up being a little bit of black magic, but it was actually relatively non-intrusive into Redis. It allowed us to kind of keep all the code that was there kind of the same, and we were able to do this wrapping in the background. There was a downside in that we had to maintain this mapping table, which had to be proportional to the size of the number of file descriptors allowed in Redis, and it introduced a little bit of thread safety issues, although for the most part, Redis doesn't really do much with multi-threaded. As you may know, in Redis 6, there's the new I/O, and this may have not worked so well with that. So the next issue that we ran into was Redis assumed that as soon as a connection is established, you can read and write to it. In this case, if you're thinking about a normal inbound connection, like a client's, once it's established, we immediately queue up the read query from client handler and wait for data to come in. This doesn't work with the TLS negotiation, since we need to also handle that negotiation part before handling regular traffic. So the solution that we naively came up was to just create a branching logic so that if TLS was enabled, we would go down the TLS path, and if TLS was enabled, we'd go down the just create file event path. This worked for the most part, but did end up introducing some duplicative logic and sort of made a complex backend of how the TLS negotiation was handled. So the next issue is an interesting one, which is that TLS doesn't interact properly with kernel polling. So the kernel polling we talked about earlier, all it really says is there data to be read from the kernel buffers, or can I write to kernel buffers? For the read case, TLS also actually introduces its own intermediary buffer. So when Redis calls a TLS read, it first reads from the TLS buffer, and then if there's not enough, it will also check if there's more data to be coded from the TLS buffer. So one last thing worth noting is that all TLS information is actually included in what are called frames, which are effectively chunks of data. So in TLS, you can't necessarily read 1 byte off the socket, but you might be able to read like 16 bytes off this, the buffer from the kernel. So this can end up in some interesting situations. If you're doing a function call where you're saying, give me up to 12 bytes of data, and you know underneath the hood that hello world's coming in this example, when you start doing this read, the TLS buffer will read the first 10 bytes off the kernel buffer, because that's the chunk it's looking for, but it's not able to fully process the 12, and it knows there's more data available in the kernel buffer. So then it will read the rest of the information off the kernel buffer, and then everything will be in TLS space. At that point, the read will go through, since we now have 12 bytes to read, and we now have our hello world. In the regular TCP case, the foo bar would still be in the kernel buffer, and so if there was a handler based on that, it would get refired. In this case, the kernel buffer is empty, since everything was read out because of the TLS framing. So our solution to this was to recall event handlers when there was data available in TLS buffers. So why do we think this is a good assumption? Because everything in Redis is driven by the event loop, which means that if there's data available in the TLS buffers, that's really kind of the same as saying there's data available in the kernel buffers. So we can basically go and say, oh, we read some data from the TLS buffer, but there's still some data left. So let's go and queue this up, and then when we can, we will go redrive this specific function to read the rest in, which will cause the rest of the data to be read in. So this is what we basically called our repeated read system. And what we use is we use the periodic job provided by the event loop in order to schedule a job to run in the future. Okay, and then the last and interesting problem had to do with how TLS has userland state, which isn't shared between processes. So as we mentioned in the previous issue, TLS has userland buffers, but it also has additional state relating to the current progress of the TLS encryption. So all of that information is needed in order to send and receive data along a TLS connection. So where does this break down? Well, within Redis, there is a way to do a replication called diskless bgsave. The way this works is when a master is trying to sync to its replica. The replica will send the sync command starting the full sync. The parents on the master will create a child process, which will go and save its content and send it over the connection to the replica. And once that's completed, it will exit. While the replica is sending the full sync, the master will be accumulating incoming writes. And then once the child process is finished, it will terminate and the master will resume sending data to the replica. In this case, the child and the master are two separate processes. So we can't transparently hand off from the master to the child and back to the master without losing some state. So we need some way to transfer the state back from the child to the parent once the full sync is done. The solution that we came up with, which arguably wasn't necessarily the optimal one, was to renegotiate TLS once the child was done writing out the full sync. The reason I say this wasn't necessarily optimal is it produced a slight divergence between how non-TLS and TLS behaved, which was one of our goals that we kind of wanted to avoid. But it was relatively performant in that we were actually using a background process to doing all the TLS, and that actually kept the main thread relatively open for handling other requests. The state we were really looking for at the time was to just send the connection state from the child to the parent, but using the library that we had at the time, we weren't able to successfully implement that. All right, so at this time, we finally had all our problems solved. We had a fully working implementation, so we submitted our pull request on April 18th, 2018, which received a lot of fanfare. As I mentioned earlier, Salvatore seemed excited about it. It looked on the outside to be relatively non-intrusive. We tried our best, given some of the earlier assumptions we made, to try to make it as little intrusive as possible. But upon further inspection, it started to become clear that there was a lot of complexity that was sort of being abstracted away that was actually pretty hard to understand and would probably also be hard to debug. So ultimately, Salvatore agreed that he was invested to getting TLS within Redis 6, and we would follow up. Okay, so part 2, complexity strikes back. So the main feedback that Salvatore gave us while we were negotiating with him was that we should try to implement one of the two alternative suggestions he had, which were to build a proxy-like implementation with Unix domain sockets or build it like a module. So this was the feedback after the 2019 RedisConf, which was almost a year after the initial draft. And at this point, he was more committed to helping us get in, and we were looking at this more seriously. So let's start with option 1, which was building a TLS proxy within Redis. So the way you can intuitively think about this is in the earlier example of the TLS proxy outside of Redis, this is just a TLS proxy in another thread within Redis. And you can see that it solves some of the intuitive problems. So if we look at inbound connections, they behave more or less the same way. Inbound connections connect to Redis. They connect to the proxy thread. The proxy thread finishes the TLS negotiation, and once it's done, it opens a Unix domain socket to the main Redis thread. It handles more or less the same it was before as the TLS proxy we talked about earlier. For outbound connections, we're actually able to build a slightly better solution. Instead of having to configure everything, we can basically use same process communication to send the proxy information about where we want to connect to, and also open a Unix domain socket. The proxy would then go and do that outbound connection, do TLS negotiation, and when it was done, it would accept that incoming Unix domain socket. This allowed us to keep a relatively simple implementation on the Redis side, since it behaves almost the same way, with just a few minor touch points. So what ended up not making this the solution we went with? And the main reason for that was actually performance. So if you think about Redis, a lot of the time it spends is actually doing system calls. So if you do profiling, most of the time is spent when it reads in data from the network and then writes data back out to the network. The actual time it takes to do most of the operations in Redis is actually really small. So the problem with the proxy is it actually triples the amount of system calls we're doing. because we have to both read into the proxy, write from the proxy to Redis, read into Redis, write out from Redis, read back into the proxy, and write back out from the proxy, which adds a lot of overhead, which is something we kind of didn't want to do. And any sort of solution that tried to use this as a starting point ended up being more complex than what we were originally proposing. Right? We could use stuff like other types of communications. We didn't have to use Unix domain sockets, but then we needed other forms of making sure stuff was eventing in that. And it ended up being more work than we really thought was beneficial. So that brings us to the next option we considered, which was module support. So Redis modules was a feature developed in Redis 4, which basically exposed a set of interfaces to define extensions to Redis. So initially this was thought of mostly as a way to add new commands into Redis, but it ended up evolving into ways to extend Redis in all sorts of different ways. One of those ways would be to expose a network interface that you could use. The problem with this in implementing TLS is that it ended up being either too simple to be useful or too complex, in which case we should maybe just do the original idea we thought of. A simple interface that just has read, write, connect, accept pushes a lot of the complexity back into the module, at which point it's maybe kind of easy to break the module support for TLS. And since we think TLS is important, it's maybe not a great idea. And then the complex interface, where we include hooks like callbacks and TLS renegotiation, it ends up just being just as intrusive. It's just pushing the code out to another place. One of the main reasons we ended up not going with this approach is that a lot of the members in the community strongly believe that TLS should be a first-class member of Redis 6, given that there will now be access control lists, which is ostensibly an authentication feature. If you can't encrypt that authentication information in transit, you can just read it over the wire and then resubmit the auth commands. So we thought that this should really be a first-class feature and it should never break. So even if maybe modules were an idea in the future, there should be first-class TLS support. All right, so now that we've gone over some of the alternatives, we are back to returning to the return of embedded TLS. So we were basically back to the point where we were trying to simplify the original implementation so that it could still meet the same use cases, but be more maintainable. This brings us to the proposal made by Yossi, a member of Redis Labs, which was to build an abstract connection I/O API. So although connection abstraction I/O APIs are a thing in other types of applications, the real standout features that Yossi proposed were that we would make sure connects and accepts were all asynchronous so that connections could be handled later. There was more first-class support around handling of the event loop, and it included a lot of Redis-like APIs in order to simplify the implementation of the TCP versus TLS implementations. So this was proposed, and Yossi went ahead and implemented this design, and it ended up working pretty well. So it was able to simplify 3 of the problems that we called out earlier. So the first issue we called out, Redis uses file descriptors as a way to define a connection. Instead, what we did was to kind of bifurcate it and look up the data later. We just rewrote it all to just use a connection. If you go look through Redis today, you'll actually find very few examples of file descriptors outside of the places that are explicitly network-based or based on the event loop. So now it's all handled kind of there, and instead of calling the real POSIX write commands, you now call connection write-based commands. Instead of read, you call connection reads. So this mostly solves all of that. The next major win that we saw was that with Redis assumes that as soon as a connection is established, you can read and write to it. The connection abstraction solved this by what we mentioned earlier, is that all connection establishment or connection acceptings include a async callback handler. So in this case, all Redis has to do is define the callback and start the connection. The callback will eventually be called if either the connection establishment fails or it succeeds, and then it can continue on as before. So instead of bifurcating the logic, we just make it so that there's an optional step that the connection can go through. This is better in that it reduces the amount of logic, but did require a little bit of refactoring. The last major issue that got solved was how TLS user land state is shared between processes. Instead of what we did, which was do a complete TLS renegotiation, the child process now proxies all of the information from the child back to the parent. So in this case, in this situation, the child's not sending any data to the replica and therefore does not update any of the TLS states. This does have the unfortunate consequence of adding CPU overhead, which we believe is something that can be fixed in the long term by just copying the needed TLS state and still writing out from the child. But it does unify the TLS and non-TLS paths, since the child no longer needs to transfer the state, and we thought that was a big win. So there's also some additional benefits as well. TLS may send other types of control messages in response to events like graceful shutdowns. Since TLS is a layer above networking, it might want to shut down the connection gracefully. In this case, a TLS connection might want to send different information than a TCP connection would, and it's nice that this allows the connection abstraction to redefine what's the current event processing looks like so that it can send its own types of commands. It's also another benefit is that the interface is generic enough to allow other networking types, including other TLS implementations. A minor point that wasn't brought up here was that there was a lot of contention about what type of SSL we want to use within Redis. AWS was a big proponent of S2N, which is an AWS developed library which has certain types of, which is better tested, has more validation, and is also just generally easier to read. But we ended up going with OpenSSL because it's more widely available. With this generic infrastructure, it's actually potentially in the future that we can also add some other SSL libraries like S2N or LibreSSL or Boring SSL. So with that, we are almost up to date. Back in October, the connection abstraction was accepted, fixing all of the major issues that were called out. And at that point, it was when we kind of called success, and we believe that TLS was actually going to get accepted into 6.0. So now we have mostly described the implementation we have today. So looking to the future, there are still many improvements we can make to the implementation we have. I do consider this sort of like a V1 of this TLS, and we're hoping that it evolves positively over time. Some of the suggestions that I have thought of are improved module support that we talked about earlier. One nice thing is that it would be great if we could load in a TLS module without having to take downtime or being able to reload TLS without taking downtime. The current implementation does dynamically link it, so you would have to restart Redis in order to update it. The next thing is better cluster compatibility support. So TLS has support for what is called hostname validation, which means when you're connecting to a remote host, you validate that the host name it says it is the same as the one you believe it to be. This can't happen with Redis cluster mode, since cluster mode is only aware of IP addresses. Within AWS Elasticache, we implemented support so that we also can show the host name, and we believe that's something that open source would also benefit from taking in. The next improvement would be PAKE, which is password authenticated key exchange, which allows to authenticate while doing the TLS handshake. This would allow us to do things like authenticate with Redis ACLs without actually having to send the password in plain text, since it would be done over the TLS. Which also allows Redis to not know what the actual password hash is, and it will validate as part of the handshake. And the last improvement, which everyone could probably maybe chip in, is improving clients so that they all fully support TLS. There are so many clients that don't fully or adequately support TLS, and I think that's someplace that would benefit a lot. Also, if anyone else has suggestions or improvements, the community still is very interested in improving this feature, especially me. So with that, I will briefly plug the service we run for, which is Amazon Elasticache for Redis. We are the fully managed Redis-compatible in-memory data store in the cloud. Recently, we've made a lot of improvements for performance. Things like our enhanced I/O allows you to achieve much higher performance and utilize some of those extra CPUs. We've also done a lot of optimizations for R5 and M5 instance types. We've also extended our fully managed and our ability to be highly reliable, and that we now supports multiple regions. You can now set up a primary region and have up to 2 secondary regions that are passive reads, that support passive reads. And as always, we also are secure and very compliant. We still have our encryption in transit support, and we're hoping to add lots of new features in the future. So thank you everyone for listening to this talk. Hope you all enjoyed it.